So axioms are just like postulates in that they are assumed to be true but aren't proven. Okay? However, they differ because they're more universally applied. And so the following axioms and common notions that we're going to go through on each slide, I'm going to give you the common notion form, so the historical translation or the historical context of it, and then the axiom or the axiomatic form, which is kind of the more modern translation of that. Okay, so let's look at the perspective historically. The first common notion that was introduced in Euclid's Elements, or the first kind of recorded geometry text, has to do with identity and equality. And what it says is that things which equal the same thing are also equal to each other. And so that's the common notion form. So if you see something that's written, or if it asks you for a common notion, it's this phrase. And so that's the first common notion. Down here are the axioms that have been built on that common notion. The first is the transitive property. The transitive property is basically an interpretation of this. Two things that are equal to the same thing. So if A is equal to B and B is equal to D. So here's two things, A and D, that are equal to the same thing, B. Therefore, they're equal to each other. So if A equals B and B equals D, then you know that A has to equal D. So this is a case of the transitive property. And it's just a strict interpretation of this first common notion. And now we can extend this a little bit more because the axiom or the mathematical rule of substitution can also justify this same relationship. So if I write this statement the same way that it appeared, so if A equals B and B equals D, then what we can do is we can take this whole original statement and we have A equals, and what can we replace B with? B is equivalent to D. So we could use this to justify as well. Okay, so substitution involves replacing one item with its equivalent. And transitive property applies this whole logical sequencing. If two things are equal to the same thing, then they're equal to each other. So let me show you a case of substitution that's strictly substitution. It's not an example of transitive property. So if you have A equals B and A plus B is equal to C, then the conclusion that you can draw based on substitution would be if we took this entire equation here, A plus blank is equal to C, what can we replace B with? It's equivalent to A. So if we use this as a replacement, the only way that we could justify this particular step would be by substitution. It's not an example of transitive property. Again, transitive property has to involve this specific relationship. It's a whole sequence of logic. Right? As we start to introduce proofs, we're going to begin with algebraic proofs, and I'll try to point out when to use transitive or substitution. But again, the rule is anytime you can use transitive property, you can justify that as substitution. Okay? However, the opposite's not true. Substitution can sometimes be used without transitive property applying. All right, the next axiom and the second axiom introduced in the Elements is one that you should be familiar with. Okay? Or again, it's a common notion because it's historically speaking. The wording is if equals are added to equals, then the wholes are equal. All this is what we went through in algebra as the addition property. Okay, so the addition property, if we convert this into the logical form, if A is equal to B, then A plus C is equivalent to B plus C. And you can add the same thing to both sides of an equation, and that's addition property. Okay, the next common notion deals with subtraction inequality. The historical wording was if equals be subtracted from equals, then the remainders are equal. Again, the axiomatic form that we have for this is just the subtraction property. If A is equal to B, then we can subtract the same value from both sides. So A minus C is equivalent to B minus C. Okay, and so really, even though it stops here as far as the mathematical operations go, any math operation is considered an axiom. Okay, so multiplication property, division property, the property of powers, the property of square roots, the properties of, again, any type of mathematical operation, so factoring and so on. Those are all examples of axioms because they extend universally to any math and science realm. Okay. So when we do get into proofs, any mathematical operation is considered an axiom. Okay, but it's not one of the original common notions unless it's the addition or subtraction. All right, the next common notion that was introduced in the elements has to do with congruence inequality. Okay, and the wording for that was things which coincide with one another are equal to each other. Okay, and so that has several implications here. It has a couple axioms and it also has some definitions. And again, the types of things that we can start using for proofs are definitions, axioms, postulates. So those are the only things that we can use until we start proving relationships. Okay, so let's start with the definition. So this really is just saying what we now call congruence. Okay, so things which coincide with one another are equal to each other. That is what congruence means. So congruence is given by this symbol, and it means equal in all respects. And so things which are congruent with each other or coincide are equal in all respects, and that's what we call congruence. And so if segments are congruent, that means they have the same measure. If angles are congruent, they have the same measures. And those are single dimension elements, so the equality in all respects will be very limited, right? It's just their measurements. However, once you start getting into two-dimensional figures like triangles or rectangles or whatever being congruent, now all properties that exist between those congruent figures will also be equal. So two congruent triangles have equal perimeters, equal areas, equal altitudes, equal angle measures, equal side lengths, equal medians. Any measurement that you can take on those two congruent figures will be equal. So that's what definition of congruence implies. As far as the axioms that relate specifically to this, one of the things that you're going to see when we start doing proofs next section is in order to work with elements in a proof, you have to have those elements introduced. So it might be part of the given state. It might be based on postulates, axioms, or definitions. And so if an item doesn't exist in a proof, one way to introduce it is to use reflexive property. And basically, reflexive property says if you have A, or if A exists, then A is equal to itself. Again, it's pretty intuitive or even redundant, but when you're dealing with the logical sequencing of proofs, you have to have a specific justification for introducing any statement or relationship. And so this is the most basic one. If you need to get an element introduced into your proof, and there's no other way to do it, you might just have to say that it's equal to itself, reflexive property. Okay. Another property based on this congruence inequality is the symmetric property, and that says that if two things are equal in a statement form, then reversing the form of that statement is also true. And so if A and B are equal, then B is equal to A. Okay. It doesn't matter which order you represent them. Symmetric property allows you to just change that order. All right, one last axiom and common notion pair to look at, and that is common notion 5, which is the whole is greater than the part. So when you're dealing with this common notion, there's really not an axiom that we will use to correspond to this. Although if you look at the relationship here, we could create a logical statement, and that is if A plus B is equal to C. So here if you have the sum of the parts is equal to the whole, then the whole is greater than either of the parts individually. So C is greater than A, and C is greater than B. Now, do keep in mind on this particular case, they're talking about the geometric element. So the parts here have to exist. So it doesn't work with a zero. So if either A or B represented as zero, this statement wouldn't be true. This is talking about physical parts of elements. So parts of a segment or parts of an angle, parts of a circle or whatever. And so the whole is greater than any individual part.